Welcome to today's Roundtable webcast, brought to you by Hazelcast, Aerospike, and Attunity. I'm Stephen Fegg, Director at Database Trends and Applications in Unisphere Research. I will be your host for today's broadcast. Our presentation today is titled Fast Data, the Key Ingredients to Real-Time Success. Before we begin, I want to explain how you can be a part of this broadcast. There will be a question and answer session. If you have a question during the presentation, just type it into the question box provided and click on the Submit button. We'll try to get to as many questions as possible, but if your question has not been selected during the show, you will receive an email response. Plus, one lucky viewer today will win a $100 American Express gift card. The winner will be announced at the end of the event, so stay tuned to see if it's you. Now, to introduce our speakers for today, Terry Walters, Senior Solution Architect at Hazelcast, Brian Bukowski, Co-founder and CTO of Aerospike, and Kevin Petri, Senior Director and Technology Evangelist at Attunity. For more information on our speakers today, you can click on the arrows under their headshots. Now I'm going to pass the event over to Terry.
Well, good day, folks. And let's talk about the latest in real-time applications and the evolution in the industry. So as data has grown, so has the computations on the data, along with business rules and regulations. We've certainly seen lots of technologies come up, such as MapReduce, only to find out its inefficiencies. So the evolution has really led us to be more reactive in our designs and our solutions. And typically your reactive solutions get into it's really about the real-time data. So big data, fast data, typically you can't have both. You pick one or the other. You can have fast data and it's really small, or you can have big data that scales out. But successful big and fast data stacks have some very common attributes, and that's what I'm illustrating here. So you have situational awareness, that's getting the right information to the right person, working off of the runtime information, not off of kind of legacy or older information. Obviously, real-time latency, doing things many times faster than what historically had been done in databases. Fast big data, it's really about having the low latency along with the scaling up and scaling out. Change data capture has certainly played a key role here, being able to work on the latest instance of that data and being able to go from whether it's a batch process or into real-time processing where it's one in, one out, where we're working on a much granular, finite transaction. And, of course, architectural simplicity, that is probably the goal, the holy grail of this. And that's both in terms of logical architecture, meaning how you lay your data out, as well as physical architecture as far as how many machines is it going to consume, how many things do I have to run, how many things do I have to own and manage. So these are the attributes you kind of want to look for. Hazelcast, we've been around about 7 years. At the meat of Hazelcast is in-memory data grid. That's we're the largest open source IMDG out there. We've got millions of servers out there using our software, lots and lots of customers. But fundamentally, in the industry, what you're seeing here is as we move software further further to the customer, in memory, you now have to adapt into obviously cloud environments, obviously, the different types of connectors. But what you're looking at is getting into what's called stream processing. So while, yes, historically people would paginate data and people would work off of batch data, but in today's world, it's really about getting into an unbounded data set. And Java, for that matter, as well as many other languages, has evolved into that. So in Java 8, you'll see that they've introduced Java Util Stream, and that's actually addressing the very demand of having big data with low latency. Because streams are much faster to operate on, because you can control how much data you're working on at any given time, and you can isolate that transaction to make it much smaller. So we've introduced a product called Jet. It's completely open source. There's no monetization of Jet. You can go to jet.hazelcast.org and pull it down. It's in all the public Maven repos. Jet is an implementation of distributed computing. So what you're getting with Jet is basically taking the Java util streams and being able to distribute it across many computers. It's a single jar file, so you're not having to worry about complex, build processes, things of that nature. It has zero dependencies, therefore it's not going to break your build process. When it comes to distributed, it's very easy to, I guess, Schumacher said, any intelligent fool can add more and add more complexity, but it takes a touch of genius to go in the opposite direction to basically simplify it. And I'd like to think that we're in that latter category. So we've got many different types of use cases when it comes to real-time applications and data processing, fast big data. So real-time stream processing is really what I've been talking about now, and that's kind of on the leading edge of application development. You're dealing with data sets that are unbounded, whether it's an HTML stream, because like I said earlier, historically you would have paginated data. You would load this web page and, I've got 1 of 25 or 6 of 12 or whatever the case is. But now it's completely, it's a forever scroll, right? Google even kind of punishes, the new Google engine actually punishes websites that use paginated data. They want to protect their user experience, so they promote sites that use things like, forever scrolls. And that comes back to the application developer. And from an architect point of view, you want to make that as seamless as possible. And that's really what Java util streams have addressed. Obviously, the problem there with Java util streams is it only works in one JVM, which is why Hazelcast has Jet, which makes whatever's working in one JVM, it makes it distributed across many JVMs, as many JVMs as you'd like. Obviously, distributed, that's distributed processing. Very simple API. We're not talking about having to do like the days when Sun introduced the enterprise Java Beans and you had to implement a remote interface and a home interface and just kind of a mess and a kind of a quagmire of application development. No, it's very simple. Streams actually eliminate code, makes your code more legible and certainly more streamlined as far as not just the readability of the code, but also when at execution time, it's dare I say, lazy. If you go through and you access a collector off of a stream, for example, it'll only hit the ones that the collector identifies. So it's not doing all the work everywhere like MapReduce used to do in the early days. It actually is more intelligent and only does the work where the data is applicable. Obviously, microservices, because like I said earlier, we're a single jar file, so that makes it very easy to embed us. It's no dependencies, so microservices love us, whether you're the Spring Boot microservices or Drop Wizard or whichever microservice platform you're looking at. So yeah, we really do bring fast big data to the table. You've got lots of different types. We've got lots of customers and all, but fundamentally, like IoT is a great example. When Amazon Fresh or Amazon To Go, where they've got the automated warehouses, they've got very granular service level agreements with telemetry devices. That means these conveyor belts are moving product, and those products are actually RFID to the switch on the conveyor belt, so the conveyor belt can speed up and slow down and change direction for that product. So that as this product is literally being automated, it's automatically pulled and processed through and pushed out to the delivery truck. It's actually, you have these very, very tight granular SLAs. So you're talking about, we're not talking about milliseconds here. We're talking about nanoseconds. So in this world, when you're dealing with nanoseconds, you have to be very, very fast and very predictable. So things like garbage collection and things like that, you have to completely eliminate. And that's where Hazelcast definitely has a really good product, and that is the high density side. So as Jet sits on top of an in-memory data grid, that data grid can be using high density memory, which eliminates garbage collection. So there's no more GC. So it becomes very predictable at scale. But yeah, working with Jet, which is working with Java util streams, allows you to aggregate data, or as I like to call it, aggravate, because it's always aggravating. But basically, you're just aggregating multiple types of strings, and these strings may be bounded. That string may have been created from a map, or may have been created from a data set, or they may be unbounded, like an FTP, or you're processing a multimedia file. You're doing keyframes and pulling out certain audio. Maybe you're doing closed caption. Things like that can be implemented using strings. You're literally just processing this sliding window of data. You don't have to have all of the data at one time. And obviously, from that, it's a flow. So from the strings, it goes to the output, and that's where you can certainly write out to, your databases or alerts or whatever you're looking for on that side. As far as key differences in the field, it's the shorter number on this is better, and basically what you're looking at is the kind of one of the industry kind of hello world applications is the word count. So you throw some words out there. It's kind of like the traveling salesperson is to doing distributed compute or machine learning, doing fitness tests, which we can do as well. But the word count is one that I know that a lot of them use. And as you can see, the MapReduce is amazingly inefficient. So you'll see that Spark and Flink do a much, much better job. But as you'll notice, Jet 1, which is our prototype, and Jet.3, which is that became generally available this month. You can pull it down from all your public Maven repos. Is half, it's twice as fast as these guys. And again, it's completely open source. It's very, very simple to use. It's literally leveraging those existing Java util standards. Nothing real, nothing special going on there. There's no interfaces that you really have to implement. It's literally using those Java util stream APIs. We work with all the cloud providers because we don't actually own the JVM. That's up for your cloud provider or your whichever process management tool you choose. It's very high performance because we are in memory. So we're working in memory. That's how we can give you big data, fast data, low latency. We run the process where the data lives, so it's guaranteed with data affinity, as well as making it idempotent, obviously. So again, it's distributed in-memory computation. Historically, you would have a stored proc or something, and as soon as you're told to, okay, we want to get rid of the stored procedure and put that business logic in Java or some other tool, then the first thing you got to do is you got to lock it, you got to fetch it, you got to mutate it, you got to put the data back, and then you have to release the lock. We don't have to do any of that because we're just like a stored procedure. We're running the process on the machine that owns the data by the thread group that owns the data. So you're given total data affinity. No more locking there. So again, this just calls out the fact that it's highly optimized. Whether you're dealing with what's considered single record or if you're dealing with batch computations, it's great either way. And of course, this is a distributed version of Java util string. The architecture, I know this is a lot to cover, but everything you're looking at is open source. Everything out there is, you can go to hazelcast.org and pull down. The Jet is jet.hazelcast.org, and the IMDG is imdg.hazelcast.org. Again, these jars are in your public Maven repos today. You can pull them down and start playing with them. Fundamentally, we've got a very rich stack. So whether you're looking for messaging, whether you're looking for storage, or if you're looking for distributed compute, you'll find it in there. Again, it's very, very much relying on the Java util. Again, speaking to the level of, remember I said simplicity not only in your logical architecture, but also in your physical architecture. So it can be embedded with your application. You included the jar, so it's going to start the server inside your application. So as you start and stop your application, these nodes are discovering and you're elastically scaling up and down. Or you can move over to client server. No real change there's no change in the code, just the instance itself. You go from a Hazelcast instance to a client instance. That's all. The actual API being the Java util or Java map, either one, that doesn't change. Again, I've already mentioned it, but the next steps, if you want to get started with Hazelcast Jet, you go to jet.hazelcast.org. You'll find a 5-minute sample out, a 5-minute getting started out there. Pretty much is almost like a hello world Java util stream example. Same for IMDG. You can go to hazelcast.com and read all about it. We've got lots of white papers and blogs and all out there. As well as if you're in Microsoft Azure, you can search for Hazelcast and you can pull our product down and deploy it directly. Same for, all of the cloud platforms at this point. Again, my name is Terry Walters at Hazelcast. You can hit me at terry@hazelcast.com. But that's pretty much the quick overview of Hazelcast. So back to you, Kevin.
Thank you very much, Terry. At this point, we're going to move on to our next speaker today, Brian Bukowski, co-founder and CTO of Aerospike.
Hi, Terry. Thank you very much, and thank you all for joining the webinar today. I'm going to talk about fast data, and that's our topic today, and what I've really seen succeeding within the companies that Aerospike has worked with to implement real-world systems in this area. One of my joys as CTO of Aerospike is the ability to work with companies that are right in the middle of digital transformation. And I get to see some of the struggles, I get to see some of the pains, and then usually the eventual successes. And what I see as I'm going through this is there are a few patterns that I've really noticed. First of all, there has to be a separation, an eventual separation in thinking between the front-edge operational system and a back-edge system. And so by thinking through what's operational, what you're going to have on the front edge, what you're going to have on the back edge, is really the key to being able to eventually have a successful system. If you try to blend these systems together, you're not likely to have a successful project. This may seem self-evident, but I think sometimes when we talk about analytics, we can get a little confused because that thing that happens on the front edge is still analytical, right? It's the capability to be able to compute, the ability to do these real-time decisions. And what I find is that each industry has evolved its own terminology, like system of engagement in retail systems, the idea of in, say, advertising, they call it real-time bidding. That's when you are making decisions, or programmatic advertising. That's that fast real-time on the front edge. Next generation operational databases are what's becoming used in financial services systems to do the same thing. So the first thing that I'd like you to think about is really think carefully about your analytics tier and how to create the right separation, because you want to have enough data on the front edge, but not so much that it becomes unwieldy and cumbersome. So you see in this slide, I tend to see people ending up with around 10 terabytes of data on the front edge. Now, if you're a much smaller company, much smaller effort, that may not be true, but I tend to see people in those kinds of numbers. The internet really has been where these kinds of fast, flexible decisioning systems were all created. So when you look at the kinds of languages in use, the kinds of stacks in use, whether it be a Kafka pipe of events, whether it be using a next generation language that's easier on programmers, such as, say, even your Node.js instead of Java, the ability to use containers. I was talking to a guy yesterday from a major retailer, and he said the reason they went to containers, again, an internet tool, was really about application agility. So that's one of the patterns that I see, people who are willing to start moving. Maybe you still have back-end Oracle systems, but the ability to start thinking with these new tools. Those are really some of the key systems that I see. And all of this comes down to Gartner analysts have talked about HTAP, Hybrid Transaction Analytics Processing. And what they're talking about is the same trend of doing more on the front edge, more with that initial data. Now, the architectures that work, again, have some separation between what's in the front end and the back end. So you may be using a Hadoop, you may be using a faster system like Hazelcast or Spark in terms of the kind of front edge, back edge you're using. But when you're making internet speed decisions on the front side, what I've seen architecturally work is this thing that I'm starting to call the one-hop architecture, which is you have this application algorithmic decision engine that is listed here. That's going to be your own code. That's going to be your algorithms, the key to your business, and that's going to need to be in your own tool set, right? If your programmers are familiar with Python, if they're familiar with Java, if this is a machine learning problem, maybe it's a machine learning toolkit. And then you need a very fast database to drive these. And by having that one hop between the network and the storage system, your database, and then your decisioning system, which is where your code lives, that's the optimal system. If you try to push too much cache into your actual code, your stateless servers, your microservice, that can be a good decision, and it works in some cases, but I've tended to find that it creates consistency issues, creates sharp edges in your architecture, because sometimes that cache overflows, sometimes that cache is inconsistent. And one of the keys then is to use a fast enough database, such as a NoSQL system. Of course, we prefer Aerospike here at Aerospike, but the faster NoSQL systems that are often in memory, or I'll talk to you about Aerospike's hybrid memory architecture as a key component. These kinds of systems, especially when using Flash, can get you up into the multi-terabyte area for your underlying storage, thus allowing your algorithms and your decisions to really have a lot more power. Now, at the number of different companies that have been in this space and have been actually capable of using this, you'll see a lot of ad tech companies. They were some of the first movers. Now you're starting to see e-commerce companies, betting companies, even telcos. They have to make a lot of decisions in terms of routing data. You'll see companies like, say, large-scale web companies. Kayak really improved their system by using this same architecture. So what this is really is what an enterprise would call the digital transformation. It's all about being able to take that key insights and those big data back-end systems and move them moment to moment on the front end. I'm going to take you through some of the examples of how this works. In the old days, we would tend to build these applications with an architecture that looks like this. There's usually an underlying operational data store. Would often be, say, an Oracle system. And then there would have to be a cache layer, because as you started adding more and more applications with that system and trying to do more and more with your data, be it decisions, be it fraud detection, be it risk analysis, the kind of streaming architectures, all of those would start putting more and more load, and expanding a traditional relational database is always a real hassle. You'd go to your DBA and say, well, I need to add a column. I need to be able to, I need a 3x expansion. And they would say, oh my gosh, that's, it's not clustered, or our rack cluster is at capacity. This is going to be a big deal. It's going to take a year. However, we can put in some cache for your application. So you'd end up with a lot of this style of application. What we're starting to see, though, is an architecture that does not have those two layers. So instead of that hop to the cache, then hop to the database, what we're starting to propose and see as a successful implementation pattern is a system that has your application and then a database directly in it, which is correct, but also fast. Now, that database may have RAM caches involved in it, but it doesn't have a cache as a separate component. Simpler to manage, more effective, better caching decisions internally. Of course, it has to be scale out horizontal, because you go to your DBA and you say, I have a new application. It also has to be scale up, because you want each individual server to be making the greatest use of its hardware. So you want a system that's capable of hundreds of thousands of transactions per second per server. Within this system, you really do have to think about price because, as we said, besides the complexity, expanding these systems previously, when you were dealing with relational engines, really the issue was, I need faster storage, right? I need to move to all flash. I need to start putting Fusion IO cards in my databases. I may need more licenses from my system. And all of those are possible. Well, it was always possible to expand your database layer. It was just hard, or hard simply due to price. And this has been one of the benefits of NoSQL in general. The premise of just about every NoSQL company is the idea that you have to have our horizontal scaling. Cassandra, for example, has been very popular in this area. And Cassandra's claim to fame is it does scale horizontally for any set of problems. And it does so easily, just add servers. However, what we find with some of those systems is the use of Java virtual machines, the use of inefficient rotational disk-based systems means that scaling is possible, it's just expensive. So with Aerospike's hybrid memory architecture and focus on flash, what we find is the ability to really do that at a much, much lower price. So I'd like to sort of whet your appetite a little bit with systems that have used this kind of architecture successfully. So within the real-time advertising space, we found that a particular company called Immobi, which is one of the market leaders in real-time advertising for the mobile environment. They're based out of India, but it's a worldwide company. They exist in all of the advertising systems. They used to keep only 4 terabytes of data on their front edge. And that worked for them for a while, and they were using really a back-end system like this shows that is batch, BI, based on a combination of Spark and HBase on their back-end, and that was about 40 terabytes. What they found was that by switching over to putting more data on that front edge, they were really able to up the capabilities in terms of being able to provide deeper and richer insights. Now, this slide doesn't show it, but it turns out on the back end, they expanded that also. So their use of a combined system using Spark and Hadoop for the data lake pattern of having petabytes worth of data on the back side, really allowed them to be able to massively expand their capabilities and to do so successfully. Now, the advertising technology world, of course, they were market leaders in this, sort of getting started with these systems nearly 6-7 years ago and really pushing the edge. And now what we're finding is companies in more traditional enterprises, but still on the leading edge, are also going through and making specific architectural changes in order to get this same architecture. Financial services for companies, for example, can use the same kind of system for their current active positions for their customers. So a particular set of customers we've worked with are ones who have really created a new architecture around being able to have an operational database, again, using the one HARP architecture. And key to their system was the ability to scale their data from, as the slide shows, about 3 terabytes, just like that previous example, up into the 10 terabyte range. Now, what this gave them was, in financial services, expanding their operational database meant they could expose the exact trade data as it is happening. In the older architectures, which were pure streaming architectures, you didn't know as a trade was settling what its current status was. In the modern world of trading, even for a customer account, you need to be able to take a block of shares and present it to multiple exchanges in sequence to see who has the best price. As that trade is settling, that minute where sometimes you say, I want to buy 100 shares of, say, Apple, you just sit there and you have a little spinning ball, trade in progress, and you're antsy, what's happening? So they found that in order to have a better customer experience, they wanted to show what was happening, how it was happening, where it's in progress, is it being broken up, what trades they're getting out of which exchanges. And all of that really turns one trade into a much richer experience. And that was one of the key applications of being able to use a database instead of a streaming in-flight system. The other requirement is the business necessity of richer and deeper risk analysis. We all know from what happened in 2008 that these companies are lenders, essentially, and that's the old margin call, when to margin call customers. And by having this kind of fine-grained information about trades in flight, if markets start misbehaving, get sludgy, trades aren't settling appropriately, these companies can now figure that out in flight on their real-time data. Now, you might have the common question, well, wait a minute, these new NoSQL databases don't necessarily have the compliance features and encryption, et cetera, that goes back the kind of years and decades that, say, an Oracle or a DB2 system has. The way around that is to still have a reconciliation and legal database sitting behind your front-edge system. So in this case, you can see there's an operational database which has to be correct. So it has to use flash, it has to use storage, it has to have high consistency, and then, but still you need a write-only database behind it. The benefit here is you can scale that operational system. You can read against it. It is correct, but it doesn't need to have all of the same compliance features because you do still have that back-end system. Telcos have also been starting to use this system, and it's been a really eye-opener working with these systems as well. So these use cases tend to be smaller in memory. I will say it sort of breaks the model that I was saying of tens of terabytes of data. It's often real-time routing information. So between billing and routing, we now know that data, not just phone calls, but actual data, packets are really what makes a cell phone, a modern cell experience tick. And all of our billing plans are now based on the number of bytes of data, not the number of minutes of cell phone plans. We're starting to see richer and richer offerings by the different telcos. Here in America, we have these streaming plans that allow a carrier to throttle individual streams and individual content sources, but then not have them count against your data plan, all depending on a customer preference. Customer goes to the website and they're expressing their preference. So it's a form of personalization, although the telcos don't see it that way. They see this as really a business offering that they can use to attract customers, free streaming. And it's not exactly free, it's just a customer preference about how to treat individual kinds of data streams. This kind of user information has to flood and propagate throughout the system of routers, and also is necessary for keeping track of billing, which needs to be now done on a packet-by-packet basis. So again, it's a form of personalization. Another interesting case is fraud prevention. And I love fraud prevention as a use because where there's money, there's fraud. Anytime you're a business making money, you have to be on the lookout for some bad actor, whether it be a partner, nefarious person, a criminal, coming in and trying to take what's yours. So I saw this originally within the ad tech companies. There's particular kinds of click fraud where you have bots going out, clicking on ads, or even a malicious website claiming to have clicks and wanting to get paid off of clicks when no users or clicks existed. And so in the spy versus spy of bots, bots that were easy to detect, bots that now look like people, you get a variety of different fraud prevention algorithms, industry by industry. Even in financial services, there's now more sophistication in terms of being able to do a lot of the time-honored techniques, but do it in a more sophisticated, internet-savvy, coordinated way. In all of these cases, we're really seeing this same kind of front-edge system. So in a retailer or a payments processor, you may previously have used a system that was a rules engine, and those rules engines are driven by back-end insights. Same kind of system, except remember back to that architecture I was talking about, the ability to write your algorithms up front and the ability to put them in your language, in your stateless server diagram, and then rely on a very large data pool. Now, maybe as a payments processor, you have access to market baskets that are risky, you have patterns, timings, locations, You may have machine learning algorithms. Several of our customers are using those to be able to try to sniff out for further analysis or to actually even real-time block different use cases where you do believe that there is fraud. The goal in these cases is always a more accurate result, because the goal is not to prevent fraud. The goal is to allow forward business that is your customers and give them a great experience to avoid both false positives and false negatives. So some of these are some of the more exciting systems that we've worked with and some of the largest scale. So hopefully that presentation gives you some ideas about architectural patterns to apply, some rules for doing fast data. Use your native languages for your team. Choose the right language for the system. Think about that one-hop architecture where your stateless servers are doing next-generation algorithms on a large core flexible underlying database and working with that back-end analytics system. So hopefully the use cases also gave you some food for thought in terms of how this can come to your business. Thank you.
Thank you very much, Brian. At this point, we're moving on to our final speaker today, Kevin Petri, Senior Director and Technology Evangelist at Attunity.
Thanks, Stephen. And thank you, Brian and Terry. Very interesting stuff. I think that there are some very interesting and common takeaways here as we look at fast data analytics opportunities and requirements. I'm very pleased to have the opportunity to talk with you a little about what we're seeing customers see. I would echo a few common themes here. Terry talked about the key components for mixing big data and fast data, for achieving fast data analytics with big data. CDC, change data capture, is one of the key components. Terry agreed with that completely, as well as architectural simplicity, looking in particular at the number of machines and number of architectural components that need to be managed. Those are two real principles that we have in terms of the technology that we're investing in and helping customers use in order to make the most of data. There's increasing research that talks about the declining value of data, and I think it's incontrovertible that there are so many real-time opportunities with streams of data in different forms that have a very short shelf life. So we've seen data recently showing that whether it's operational or tactical data, depending on how you define that, within 5 minutes, most of the value of that data could be gone. And maybe that's someone standing in a retail store or online who has made a transaction and is available right then for a cross-selling offer. Maybe it's a real-time fraud check for a credit agency. Maybe it's a real-time customer view for an insurance company. Those are all things that we help customers address, and there's no question that that data has a very short shelf life, a lot of it in terms of capitalizing on value. So what we boil things down to in terms of fast data integration requirements are three particular things. The first is the need to ingest or replicate data on demand. Now, what I mean by that is that oftentimes opportunities to capitalize on data can arise quickly, and so you need to be able to configure your system, your architecture, in this case your replication commands, quickly in order to make the most of data set A and move it into platform B for joint analysis with data C, just for example. The real-time streaming is a key component here, near zero latency data transfer. And another key component is being able to load across increasingly heterogeneous environments. Targets are proliferating. So we talked about Cassandra, we have Hadoop, we have Kafka. We have environments like SAP that want to take advantage of Hadoop and Kafka and cloud platforms. All those things mean that you really need a single portal or capability, if you will, to move data across those heterogeneous multi-platform environments. So those are some of the most pressing requirements that we see. The challenges, of course, are that a lot of data transfer capabilities conventional data extraction, transfer, and loading commands, or ETL commands, take complex, repetitive manual coding. It takes time. It's error-prone. Another is that data transfer often has higher latency than organizations are willing to bear and can impact source production performance. And a final point here is that because oftentimes replication tools are limited, you might have one process to integrate data from platform A to platform B and another process entirely to integrate data from platform C to platform B. That doubles the administrative overhead when you have situations like that. What we've developed and enable customers to use is Attunity Replicate software. And we really strive for simplicity. By that I mean automation in particular of the entry of data extraction and loading commands. We have award-winning change data capture CDC technology that will use one of several different methods, depending on the sources and targets and requirements, to move data at near zero latency from one platform to another. Through tight partnerships built over decades with all the major data warehouse, database, cloud, and Hadoop vendors, we have the ability to tightly integrate with all those platforms as sources and as targets with the same process. And so I'm going to talk about that universal portal to your data sources and targets. We are the #1 independent provider of streaming CDC. There are alternative tools, and we won't get into competition too much here, but there are alternative tools that are really more beholden to certain platforms than others because a platform vendor promotes them. And so our existence and position as Switzerland is really a benefit there. Okay, so let's talk about automation and what we mean by that. There's really no manual coding or scripting that's required in order to identify a data source, identify the tables or other data sets that you want to move, and then move them from source to target. While you execute, you can automatically monitor. This is end-to-end automation. You can configure very easily exactly what type of data transfer makes the most sense for your environment. So the target schema is going to be created automatically based on source parameters. We can automatically map heterogeneous data types and DDL changes that happen to a source. Maybe it's new or changed tables or columns, automatically can be propagated to the target. So these are all ways in which a lot of those little cascading pebbles in the pond that can create a lot of waves can be easily absorbed and keep things simple and keep architecture simple. Okay, so the interface here, again, think command line interface being replaced completely by a web-based graphical user interface. It's a point-and-click interface, so you click to replicate, you select your target, you select your source, you select your data to move, you click to execute. You have wizard-assisted configuration steps, and this is a consistent process for all sources and targets, whether it's Teradata, DB2, what have you on the source, Hadoop, cloud, Amazon Redshift on the target. It's going to be the same consistent process, which really gives you that universal flexibility. Again, getting back to the notion of a simple architecture, a lot of this gets down to, as Terry said to us, the number of machines that you need to worry about. We have a zero-footprint architecture, which means that on the sources and targets, no agent software needs to be installed. Rather, we have an intermediate piece of software that will scan source transactions, real-time updates as they come in. It'll read change logs in order to identify any real-time transactions that need to be replicated with change data capture from the source production system to the target. And that can enable real-time analytics without interrupting source operations, without creating any administrative overhead on the source, because when you install agents on hundreds or potentially thousands of source systems that are feeding a data lake, the requirement to update all those agents can really create prohibitive levels of complexity. That's not a requirement here. We're removing that agent headache. Okay, so this is a quick overview of change data capture options that we have. We can sequentially copy transactions from point A to point B as they come in. We could also, based on the connection and what's appropriate for latency, we can batch together a set of changes and move them from source to target. We can also integrate with data warehouse native loaders for ingestion and merging. Or, and I'll talk about this more, convert transactions on a source database to an event stream in order to adopt messaging that goes to Kafka message brokers. So this is a little bit more about Kafka. Kafka is a very popular way to create a data stream and capture value at the moment of data creation. A lot of different examples here. I talked about real-time fraud credit checks, the real-time customer view, real-time location-based customer offers. Those are all examples of ways that you can take advantage of data streams, oftentimes that are going through Apache Kafka message brokers. What we will do is copy data, potentially in batch or with CDC, and we'll stream it as a set of events, a set of transactions. It's converted to the JSON or the Avro data format, and it will go to the Kafka message broker, which in turn can broadcast that stream to one or more big data targets, each of which could perform a different set of real-time analytics on that message stream. So it's a pretty powerful set of capabilities here. And the key points that I'd make about what we're doing is we're simplifying the process to move data real time from point A to point B. And again, this is part of our universal coverage of platforms. I won't go through all the platforms that we support, sources and targets. I think we're about 36 altogether. But the idea here is that we've optimized for the source with our log-based CDC that does not interfere with production transactions on the source. We have batch APIs as well. When we're moving data over the wide area network, I have a bit of a cold, excuse my voice. When we're moving data to a cloud repository over the wide area network, we can create multiple encrypted paths that move in multiple paths across the wide area network in order to reach the target with high performance and in a secure fashion so that data integrity is ensured. And we talked about the different CDC options we have and the ability to integrate with native data warehouse loaders. Okay, SAP is an environment we are very familiar with. We have been working with the SAP organizations for a number of years. Again, forgive my voice. As I said, I have a bit of a cold. What we are now able to do is look at data that's been created by an SAP application, looking across all core and industry-specific SAP modules, and we can copy documents, transactions, and business data out of SAP into any of the targets that we support. Relational databases, data warehouses, Hadoop. We can replicate data into HANA, and we can do this on-premises or in the cloud. So this means that we can decode SAP data, which has complex source structures, in order to enable, on the target, business users to analyze that data in context. And I'll talk more about what exactly that means. We can look at custom tables, pool tables, index tables, and we can deliver them to the target in a format that is easily used, let's say on Amazon Redshift, a popular target, or Hadoop as well. This is really unmatched right now, and it's creating all kinds of compelling new analytics use cases for SAP organizations. Okay, let's talk about Hadoop. Hadoop is a very popular target, and we're working with a number of large organizations that are engaged in massive data consolidation efforts from hundreds or potentially thousands of sources into an enterprise data lake. They can stream data with CDC from any major source into the Hadoop file system or Hive. The data then is available to be used in HBase or by Spark. I talked about automated schema generation. That applies here as well with HCatalog, and we will integrate with native APIs so that there are no external adapters or custom code required. Key points here are that we'll integrate data from any major source into that Hadoop data lake. Just a little bit about us. Our mission is to enable IT to deliver more data ready for analytics to the business. And we have a fair amount of traction. We're very pleased to work with half of the Fortune 100, 7 of the top 10 manufacturers, 5 of the top 10 banks, and we continue to help them with major new initiatives that address Hadoop, Kafka, and other real-time areas. Thanks. Stephen, I'm going to hand it back over to you.
No problem. Thank you very much, Kevin. Thanks for being a trooper, and hope you feel better soon. So at this point, we're going to move on to questions from our viewers today, and the first question is for Terry. Terry, so if we wanted to get started with Hazelcast Jet, and we go to that link you provided, how quickly could we have it up and running? And also, how big is Hazelcast Jet?
Well, sure, that's great. So if you go to jet.hazelcast.org, you'll see there's actually a 5-minute startup, so you can literally have this on your machine and running within 5 minutes. And that kind of plays into the second question there. The size, to put it in an old, I've got over 20 years experience, so I can say this. We can put 6 jets on one of the floppy disks, but they don't make anymore, right? So it's 250 kilobytes. That's how big Jet is. It's very, very small, very tight, and very fast.
Understood. Thank you very much, Terry. Brian, our next question is for you. How would you use Aerospike and machine learning?
Yeah, that's a great question, because people who are trying to do new next-generation systems to find patterns are finding machine learning to be very successful. So what I find most people doing is simply using their own libraries. Again, bring your own library, bring your own language. I do have some people using platforms such as H2O.ai or Spark, etc. You'll need some of that behavior to be in a behavioral store. You'll also need a model store. This is underappreciated usually, the ability to keep each of those models in an in-depth system. So you're going to need databases for both of those, and Aerospike might be a great choice for each.
Understood. Thanks, Brian. Kevin, our next question is for you. Can you elaborate on the different types of CDC that Attunity supports?
Sure. Happy to, Stephen. I've had a little water here. There are a few different options, and I think the key point is that there's flexibility to meet varying business requirements. We have Transactional Cdc, which is critical when the enterprise requirement is really to maintain order integrity, so transaction by transaction. If you need that transactional integrity, and that's more important than maybe a little more latency, then we can do Transactional Cdc. Batch CDC will bring together a set of transactions and relay them across to the target, and it'll do it in a way when you need high transaction rates and low latency. When you have high transaction rates and need to achieve low latency. Data warehouse ingest merge means that we're following the same step as batch CDC, but we're also leveraging the target data warehouse's native utilities, which are performance optimized as it delivers the data. The final point here gets to Apache Kafka, which we talked about in some detail, and that's the message encoded CDC. So we'll convert source transactions or a bulk of data into a series of events that run to Kafka message brokers. Here we'll support multi-topic or multi-partition data publication, and that creates a range of real-time analytics use cases as we talked about.
Understood. Thanks, Kevin. Terry, back to you. You mentioned Hazelcast Jet, but we are familiar with Hazelcast in-memory data grid. What's the easiest way to get started with that first?
Well, sure. I mentioned jet.hazelcast.org. You can just go to hazelcast.org or hazelcast.com, either one. But Hazelcast, the in-memory data grid, which is, I think we're celebrating 7 years now, and we're in all the telcos and so on and so forth. But fundamentally, just you can go out to hazelcast.org, and you can be up and running very quickly there as well. I think Philippe said 5 minutes. I think 5 to 10 minutes is pretty appropriate. It's a single jar file. It's in all the public Maven repos. So you can grab any one of the samples there, or you can go out to GitHub, and all of our sources, along with, really at this point, it's thousands of examples, are out on GitHub.
Understood. Thanks, Terry. Brian, our next question is for you. Would you recommend Aerospike for blockchain use in financial services?
Yeah, that's a great question. I get a lot of discussions about blockchain these days. And, I think it's a mixed bag, honestly, because the kind of system for a blockchain is a modest data size by these new standards. It's often less than a terabyte. The benefit of using a database like Aerospike is the low latency, so you can skip through the blocks and do a very efficient traversal. And the benefit is the kind of persistence that Aerospike has in order to make sure those transactions are fully recorded. So it's a pretty good choice.
Understood. Thanks, Brian. Kevin, we have time for one more question, and it's going to you. How do you ensure SAP data is usable at the target?
Great question. So SAP data environments are pretty complicated. They span a lot of different modules. You have business rules that might be not transparent to the user. What we do, and this is with SAP certified technology that we've had some time, is we replicate data from the SAP source. We're able to, in the process, convert it from the SAP hierarchical format into the source format. Let's say it's a relational format. We also can, as we do that, take the SAP terminology and apply it to the new columns, the new tables, so that you're looking at data that's been reorganized but still retains the original context about its source structure. So that's ways that SAP data can be made usable. If you're going to move it into a relational database, as an example, we'll perform a similar type of conversion so that SAP data can be very usable in Hadoop, which is also an increasingly appealing option.
Understood. Thanks, Kevin. That is all the time we have for questions today. We apologize that we aren't able to get to all your questions, but as I stated earlier, all questions will be answered via email. I'd like to thank our speakers today, Terry Walters, Senior Solution Architect at Hazelcast, Brian Bukowski, co-founder and CTO of Aerospike, and Kevin Petri, Senior Director and Technology Evangelist at Attunity. If you would like to review this presentation or send it to a colleague, please use the same URL that you used for today's live event. It will be archived, and you'll receive an email tomorrow once the archive is posted. Plus, if you would like a PDF of this presentation, you can click on the resource icon at the bottom of the console. Now, as we stated earlier, just for participating in today's event, someone would win a $100 American Express gift card, and the winner today is Bill Marsh. Bill, we will be in touch via email so you can claim your prize. Thank you, everyone, for joining us today, and we hope to see you again soon.